Okay, today is our first day of Introduction to Solutions for our new unit, Unit 10. So this entire unit, solutions. Everybody should be pretty familiar with the term solutions, and hopefully as I'm going through and doing these notes, most of you will realize that you see solutions every single day in your life. So first off, we have this mixture comparison chart. Now, I'm not going to go in depth over all of this, but I would just review and look over, okay, just this entire chart. This is just kind of talking about really the properties, difference between a solution, colloid, suspension, okay? Now we're really going to get into really way more in depth of a solution, and this is a homogeneous mixture, also known as a solution. Again, homogeneous mixtures are the same throughout, so they have very small particles that are dissolved in another substance. So we have a couple of vocab words. First one being when something is capable of being dissolved, meaning that when you place it in water, it will dissolve throughout. That is known as soluble. So we know when something is soluble, that is capable of being dissolved. And if you remember, when something is soluble, we use that symbol of aqueous. So you can remember right here, soluble in water. That means that it will dissolve in water. You should be familiar with these. We've used our solubility rules before. Now looking at when something is being dissolved. So there's two components. There is a dissolving medium, the substance that is actually doing the dissolving, okay, and in this case it tells you that if liquid water is involved, it typically will be the solvent, and that is known as solvent. So the solvent, again, is what is doing the dissolving, whereas the substance that is actually being dissolved, that is known as the solute, okay, substance that is being dissolved. So let's look at a common example of salt water, okay? In salt water, we have two components, salt and water. So when we think about what is the solute versus the solvent, okay, in this case, water is present, so you can use this little helpful tool. Ask yourself, is salt dissolving water or is water dissolving salt? Okay, we all know that salt dissolves in water. That would make salt our solute and water our solvent. Now, it's okay to sometimes think that solutions always have to be a solid dissolved in a liquid, but actually that is not the case. So we can have many types of solutions that involve all three phases. So I'm just going to kind of go through and talk to you about some of those that you might not be familiar with. So we can have a gas-liquid solution, and a really common one that most people are familiar with is soda. Okay, so in soda, we can break that down into our solvent and our solute. So in soda, our solvent is actually water, and our solute is CO2. An example, a very, very common example of gas is actually what is all around you right now, air. Okay, so in air, again, we break that down into a solvent and solute. Our solvent is actually nitrogen gas, and our solute, there's actually a good amount of them. I'm just going to write down the main three. Oxygen gas, carbon dioxide, argon, and then I'm just going to put ... because there's a lot more. Okay. Liquid. Okay, this is a example of a liquid is actually a very common household liquid solution, vinegar. Okay. Vinegar is actually another name, the chemical name is actually acetic acid. So when we break this down to our solvent and our solute. Okay, our solvent is water, and our solute is actually acetate. So hopefully as you're looking at this, you're realizing a lot of these solvents are water. Now solids, this one's a little bit harder. When you think of a solid, you're thinking of two solids that can basically, dissolve into each other and form. So this is actually an alloy, if you are familiar with that. An alloy is a mix of metals. Okay, so for this specific alloy, we're going to actually look at 14 karat gold. Okay, our solvent is actually gold, and our solute is silver. Okay, now you just need to be able to be familiar with if we were to ask you a question, what one of these would be an example of. Okay, now moving on to solubility. Okay, looking at what is solubility, okay, and how we actually look at those particular things. So solubility is how we can change how much and how quickly we can dissolve something. So the amount of solubility refers to the maximum amount of solute that will dissolve in a specific amount of solvent at a specific temperature and pressure. Okay, now this is different from affecting the rate or speed, so you have to make sure that you can distinguish between that. But we're really here going to just talk about factors that affect the rate. And when we say rate, we're meaning speed. So how fast can something dissolve? Okay. So first we're going to just do a little definition. So this is dissolution is the process of the solute dissolving in the solvent. Okay, make sure you know that. That is a very important vocab word. It's the process of the solute dissolving in the solvent. Now we have three ways that we can speed up the rate of dissolution. Okay, first way is agitation. Okay, agitation. So that agitation, you can think of when you stir it. Okay, that's going to increase the contact between the solute and solvent. Next is increase the surface area. Okay, so that's saying smaller pieces. Okay, and what I mean by that, so that's saying crush it. Okay, an example of that is if I have a sugar cube versus granulated sugar, and I place both of these into tea, not hot tea, just normal iced tea. Both of them will dissolve, but my granulated crushed up sugar is going to dissolve a lot faster because it's exposing more of that sugar crystals rather than my sugar cube. And then finally the last one is if you increase the temperature. Okay, so heat it. So this is a really good way to remember it. Heat it, crush it, stir it. Heat it, crush it, stir it. Heat it, crush it, stir it. All of these will affect the rate of dissolution. And hopefully, because we just finished our thermochem unit, you understand that why we would increase the temperature is in relation to kinetic energy, which we know kinetic energy is movement. So when we are making sweet tea, the best way to make sweet tea is have your temperature be super hot add your granulated sugar and then stir it. Okay, so now we're going to talk about saturation levels, okay? And the saturation levels we will talk about again with solubility curves, but these are first just going to be some definitions. So we have 3 types of saturation levels. When something is saturated, it contains the maximum amount of dissolved solute for a given amount of solvent at a specific temperature and pressure. So this is saying that you have dissolved everything that a solubility chart says you can. So if it says you can dissolve 30 grams and you dissolve 30 grams, saturated. When something is unsaturated, this contains less than the maximum of dissolved solute for a given temperature and pressure. So you can still dissolve more if you wanted to. Okay? So if you put solute into a solution and it completely dissolves, your solution is unsaturated because you could still add more and see if it dissolves. And then finally, supersaturated. Okay? This contains more dissolved solute than a saturated solution at the same temperature. What you have done is you have heated up the substance, added more sugar, and then cooled it down slowly. So this is your perfect example of sweet tea and how we make sweet tea. All right. So next topic we're going to be talking about is electrolytes versus non-electrolytes. Now, probably most people are familiar when you think of an electrolyte. You think of Gatorade, okay? And Gatorade is actually not lying to you. They do, Gatorade does contain electrolytes. Not as much electrolytes as other substances we have, but they do. So what becomes an electrolyte? So when you have a substance that dissociates, okay, and this word dissociates means that you break apart into ions, okay, keyword ions. Okay, ions we know are charged particles. We can have anions that are negative, so it's a negative charge, and cations, which are a positive charge. And all this happens when they are dissolved in water or melted or anything like that. So again, this is an electrolyte. Okay, so in order for something to be an electrolyte, they have to break into their ions. In order for something to break into ions, that means that they have to have a charge. So a helpful hint is any soluble, which means it can dissolve in water, ionic compound is an electrolyte. Now, how we can figure that out is we know, for starters, an ionic compound. Okay, let's just do a little refresher. Ionic compound. That can be metal plus nonmetal. Metal plus polyion. That could be a polyion plus a nonmetal, or a polyion plus another polyion. Okay? Now, again, in order for them to be an electrolyte, they have to be soluble. So you would have to look at your solubility chart, because if they are insoluble, then they will not dissociate. They will not dissolve. So a common example is NaCl. Okay? And I'm going to show you what this looks like when it dissociates. So what this is showing is when I have NaCl, it's going to dissociate into its ions. Sodium has a +1 charge. Chlorine, -1. Okay? So it broke up into its ions. An ion again. Element with a charge. Okay? Element with a charge. Another example, MgF2, magnesium fluoride. So this break up into magnesium. And fluorine. And then of course, we'd have to balance this. Okay. So these are both examples of electrolytes, okay? Ionic compounds. Now non-electrolytes. Sugar is an example of a non-electrolyte. Why do we think this is? Okay, well, sugar, okay, is C12H22O11, okay? Sugar is covalent, okay? Now we know, now you might be thinking to yourself, well, sugar dissolves in water. It does. So when sugar, that is solid, dissolves in water, it does not dissociate though, because there's no charges. So when it dissociates, well, when it dissolves, it just becomes a solution. It does not dissociate. Okay? It does not dissociate. There is a big difference between dissociation and dissolving. Make sure you know that. Okay? Last thing on electrolytes. It says tap water will conduct electricity while distilled water does not. Propose an explanation for this. So, tap water that you just get from the sink, okay, is just comes straight from the sink. And you have to ask yourself, well, what is in that tap water? Well, in tap water, there are minerals. Okay? Minerals that contain ions. Ions that will conduct electricity, while distilled water does not. Okay? Next topic is polar and nonpolar. So polar, okay, can be referred to, you can figure out if something is polar based off of if it is symmetrical, unsymmetrical by drawing a Lewis dot structure. Water is polar always. So we have a term like dissolves like. That means polar dissolves polar. That also means nonpolar dissolves nonpolar. But polar does not dissolve nonpolar. So we know that water and oil, you can look at this picture, water and oil do not mix. So if water is polar and it does not mix with oil, what does that make? What kind of solvent is oil? Nonpolar. How do you know this? Like dissolves like. So you can see right here, here's my oil. Here's my water. Okay. Now let's look at NaCl. Okay, we talked about NaCl up here. NaCl is salt. Okay, does salt dissolve in water? It does. We talked about that over here. Well, if water is polar, and we know that salt dissolves in water, that means that salt has to be polar, because like dissolves like. All right. Next topic. Pressure. So, pressure can change, has very, very little effect on the solubility of liquids or solids in liquid solvents. However, when you have an increase in pressure, you increase the gas solubility in liquids. Okay? So, again, what this is saying, when you increase the pressure, and this is all referring to a gas, when you increase the pressure, you increase the solubility. And vice versa. If you decrease the pressure, you decrease the solubility. This is known as Henry's law. So we have two soda bottles. A brand new soda has high pressure and high gas concentration, whereas an open soda has decreased pressure and decreased gas. So before a soda is open, let's talk about describing the pressure and gas concentration inside that bottle. So when you have a bottle that hasn't been opened, pressure is high. Okay? Because the pressure is high, your gas concentration is high because your molecules are tightly packed. But when you open your soda, your pressure goes down. Gas concentration goes down because your gas molecules can escape. So it says, using Henry's law to explain why a bottle of soda goes flat after a few days of constant opening and closing. So we're going to use these words. Okay? So we kind of did this a little bit earlier. So when you open your bottle, okay, when you open your soda, pressure decreases, CO2, which is your solute, escapes from your H2O, which is your solvent, causing the gas concentration to decrease. Alright, so we used pressure, we used solute, solvent, gas, and concentration. Last little topic is temperature. So we already know that when we increase the temperature, we increase the solubility of solids in liquids. Okay, so for a solid, when you increase the temperature, you increase solubility. Okay, that's what we talked about with sweet tea. However, when you increase the temperature in a gas, you decrease the solubility. Okay, think about any time you've ever had a soda. Your soda always tastes better when it is in the fridge and cold versus when it is warm. So it asks you, should you store your open soda in the fridge or on the counter, and why? Okay. In the fridge, because your temperature is low, which means you have high gas solubility. Okay? What this means is, aka, a more carbonated soda. Okay? So, really big thing, okay, is understanding that pressure has no effect on solids. It only affects gases. And you want pressure to be high to increase the solubility. When it's low, you decrease the solubility of a gas. Whereas temperature affects solids and gases. Temperature has a when you increase temperature in a solid, you increase the solubility. Whereas if you increase the temperature in a gas, you decrease the solubility. Okay? So we're going to do a little review of what I just taught you. So it's what factors affect the rate, again, the rate of a solubility of solids in water. So again, this is that heat it, crush it, stir it. Okay? So temperature increase surface area, and agitation. Okay, all of these things will increase the rate. Last thing is, this is just asking us to, I'm just going to kind of like, I basically just want you to draw the graphs of what the effect of temperature and solubility will have. So we're talking about a gas here in temperature. So with a gas, when you increase the temperature, we know that our solubility decreases. Again, with the gas, when you increase temperature, you decrease solubility. Okay? Whereas a solid, when you increase temperature, you increase solubility. For pressure, for a gas, when we increase pressure, we increase solubility. And for a solid, basically, you can just put this. It really has no effect on solids. Okay? And those are your notes for day 1 for Intro to Solutions.